Okay, so we've got accuracy and precision, and again, you guys were pretty solid on this. We'll explore it more in our own measurements and in homework. Okay. So inaccuracy comes up two different ways. There's method error. You can call it pilot error. Basically, you're not doing a great job making measurements. This is my problem when I take measurements. I struggle with getting the line right. I have to close one eye. So if you take the same measurements, or attempt to take the same measurements, but you take it two different ways, and you probably saw this in your lab. Did you get some discrepancies with your methods of measuring? Yeah. So two different methods can yield vastly different results. Whenever possible, if we need to replicate measurements, we want to make sure that we're replicating method. And I know there was one group that said, we know we have the right cylinder, but when they measured with the string, they wrapped it tight and then measured it loose, or vice versa. Yeah, they measured it loose or wrapped it loose and then measured it tight or something. Yeah, two different methods. So you have to replicate method, which means putting detail into your method. In Chapter 2, you will write a lab procedure where you have to write a procedure to make measurements that somebody else could follow. And if you don't do a good job describing the method for taking measurements, then you lose points on that procedural part of the lab because nobody else could follow it. Being sloppy. Just being sloppy, and this happens all the time. You're rushing, you're hurrying, you just don't care. And so you don't get very accurate methods. And then there's parallax. So I would invite you all to stand up and pick an object in the room on an opposite wall from you and cover it up with your thumb. Close one eye and cover it up with your thumb. Now, change the eye that's closed. What happens? It's not covering up the object. Your thumb seems to jump. Now, here's the next thing I want you to do. Pick something much closer than that, like the person standing near you's face. Okay, which one has a bigger jump? The thing close or the thing far away from you? Farther away. The farther away the object is from you, the larger that gap when viewed from, your eyes aren't all that far apart, but you're essentially viewing it from two different vantage points. You can go ahead and have a seat if you want. That phenomena is called parallax. It's actually used in astrophysics to measure the distance to to suns. So if you take two observatories on Earth, if you have observatory A and observatory B, and they're both measuring a star out here, if we know the distance between these two observatories, and and they triangulate and they do a whole bunch of math that's way beyond me, but basically their observations of this object in relationship to other objects are going to vary, and based on how much it varies, they can determine how far away that object is. Like I said, the math is light years beyond me. But parallax is also a way that you can get measurement error. My eyes don't work together well, so it's extreme parallax. I have a bigger parallax than most, I guess. So when I'm measuring something, if I don't close one eye, the lines jump around. I have to close one eye, and then if I forget and close the other eye, the next time my measurements don't match. That's a source of error. If your eyes don't work together very well, and so you can't form one image at close range, you're going to have measurement error. That's something that will get you inaccuracies. The other one is damaged instruments. And I will use the chemistry example. We have a couple balances that stick, and if you had, most of you had chemistry last year, we have lots of them. I'm sure Mrs. Haylett has some too. You think that it's balanced, and then you realize, no, it just stuck. So damaged instruments can give you instrument error too. We have in here some, let's see, what could we call these? Heirloom meter sticks. Good heavens, these things are probably 20 years. They're older than you, okay? These meter sticks are older than you. And the ends get worn down. So I tend, when I'm measuring with one of the precious family heirlooms here, to start at the 10, not the 0. Because that 0 may be worn down. That might not be a full millimeter on the end. You may have worn off an entire millimeter of instrument in the intervening 20 years of students abusing it. So that's another, it's a damaged instrument. You know, damaged or faulty instruments. I have I bake bread a lot, and I found this fantastic method. Never tap, it's like the best bread I've ever made in my life for the last 2 years. It's seriously, it's amazing bread. And you tell how it's done by temperature, which as a science person, I love. I'm like, ooh, data, numbers, cool. So I have a oven thermometer probe, and I stick it in the loaf at 15 minutes, and when the loaf reaches 190, it's done. You don't tap it, you don't thump it, you don't worry about it, it's done. Well, I had some cheapy oven thermometer that I bought from Aldi's. It was their little like homewares series, and I was like, oh, $5 oven thermometer, okay, I'll try it. And I stuck the probe in, and the first time it worked, and it beeped when it got to 190. And the next time I stuck it in 15 minutes after the loaf was in the oven, and it beeped immediately, and then the temperature kept climbing, and it got to 302 degrees Fahrenheit, and I was like, no. That's a faulty instrument. You know, the instrument is malfunctioning, you're getting a bad reading. So with accuracy, when you're measuring, you can't ever leave your common sense at the door. You have to look at your measurements and continually ask yourself, is that reasonable? Does that make sense? We do a lot of measurement in here, especially in the first half of the year. And one of the things I really want to encourage you to do in your lab groups is question one another. The best lab groups are continually putting one another on point. Wait a minute, did you catch that? Are you sure it stopped there? Let's do that again. I want to see that again. No, your tape mark, I don't think your tape mark's right. No, I saw her, she put it down correctly. Pick at one another, not in a mean way. But work together. Be on alert. Be thinking. Whether there's method error going on or whether you have a damaged instrument, we had the battery-operated cars we use for constant velocity. 1 year, one of them, basically I had a group that went out, got their data, they came back, they looked at their data, and they came to me and they said, our data's bad. Okay, why? Because it was supposed to be moving at constant velocity, it wasn't. Okay, and they problem solved, and they figured out that we had a little battery holder in place, and the battery holder was slipping. And so the car would speed up and slow down because it was getting different amounts of current. And so the wheels were moving at slightly different rates, so it wasn't a constant velocity car. Don't leave your common sense at the door when you're doing measurements. Think. Okay, I think. Here's where we get to talk about precision. It is related to the limitations of the instrument, and I would like, here, we'll just pass these around. Measure something. Darn it, this is where it is nice if you all have the same thing. Grab a physics book. Go grab a physics book. Katie, give me your measurements. You want to do width first or length first? Okay.
I got 10 and 5, 6, 6. And then
Whoa.
30 centimeters.
Science. You're okay. 26.0 centimeters. And for width, 20.5. Okay. Actually, you know what I should do is I should make a table here. Ha ha. $20.5. Okay, who else has got length and width? Go for it.
Length is 26.10.
26.10, okay.
And then the width is 20.75.
Ooh. Okay. Who else has got length and width? We're going to have some different answers. That's okay. Read.
26.15.
26.15. 20.75. Okay. Emily. That's Emma. Sorry.
26.1.
26.1.
And then 21.
21.0. Okay. Glad you added that. Okay. Kenzie? Length, if you'd be so kind.
26.20.
26.20.
20.70.
20.70. Okay. Anybody else? Any takers? Yeah, underneath, going once, going twice. Okay. Do we have enough of a representative sample? We got 1, 2, 3, 4, 5 sets of measurements. But they're not all the same. Do they all hover around a value? How would you test that? Take the average. Does the average lay inside that range? Yes, then they're all hovering around a particular value. Do we have, so what differences do you notice in the measurements? Other than some are larger, some are smaller. One thing should jump out at you. Go for it.
A few numbers were found 2 or 3 times.
Okay, we have a few numbers that are repeated. So if I'm always terrible at the stat stuff. That would mean if we had, let's see, mode mean, and no. The most common measurement, the most common value is the mode, right? Yeah, okay. So we do have a mode that appears more than once in here.
Do we?
We're measuring textbooks.
Measuring textbooks?
Uh-huh. Okay, so we have some measurements that recur. We have an actual mode. We have something that repeats on each side. And do those line up? No, they don't. Well, that's interesting. So we have this and this here, and this here. Interesting. What's one other thing you see? It's the first thing that jumped out at me because, of course, I know where we're going with this. It might not be the first thing that jumps out at you. Who? 21. Okay. Yeah, that's definitely that's the top of our range on the width. I mean, we're within what, a half a centimeter of range. That's not a big range, but that's 5 millimeters. Sig Figs. Who here remembers anything about Sig Figs? Not a hand. Okay. When you have any instrument, you can measure out to one more decimal place than the last marking on the instrument. Take a look at the instrument you use to make your measurements. What are those little teeny tiny lines in between the centimeters? They are, in fact, millimeters. Oopsie, what did I do? All sorts of silly stuff. Cut. Okay. So if, oh, hey, convenient enough. 2, 3, 4, 5, 6, 7, 8, 9, 10. I can actually, if I'm measuring something here, and this is 1 millimeter, and I have an object that lands here. What do I call that? How do I write down that measurement? How do I record it? It's probably, yeah, it probably edges past. I was intending that it was 1.5. It probably is edging close enough. You know, it lands here. Yeah, I'd say that's 1.5. You could have an argument about it. I would entertain arguments. Anybody care to argue about it? You're allowed. Huh? Oh, were you going to say 1.75? 1.75. Excellent. That was exactly the answer. That was exactly the not right answer that I wanted somebody to use. So here's the thing, and I have seen various percentages. I'm going to share with you the perspective that that was always sort of enforced on me, and that I think makes the most sense. In a measurement that small, unless you are a robot with caliper eyeballs, well, you know, show me your bionic card and I'll believe you. You probably aren't good enough to say that is 1.75. So you could say it's 1.7, but you can't go that extra decimal place. You can only go one more decimal place than the last marking shown on this. So you can say this is 1.5, 1.6. Whoops, I'm using the wrong color here. Yeah, I might even go 1.6. There are folks who will say you can only use a 0 or a 5 in that last, it's called an uncertainty digit, that you can only say, yeah, it's about halfway, or yeah, it's all the way. And that's actually what I grew up learning, that uncertainty digit's always going to be a 0 or a 5. It seems that the more modern take on that is that as long as the sort of set of measurements is, as long as the spacing is large enough, I mean, I think you'd be hard-pressed to do it on those millimeter rulers. You could say 1.6, 1.8, you know, you can use another number, but you can only go one decimal place. So you could never say 1.75. If you felt strongly that it was 1.75, you could say 1.7, you could say 1.8. But you can't go that extra decimal place. Does that make sense? Okay. Sig Figs are what we use to keep track of how precise our instrument was. So if you measured your book and you said it was, and Emily, you corrected yourself, you said 21 and then you said 0.0. That's got more precision because you're saying, hey, my instrument goes out to at least centimeters. And I'm saying this is dead on 21 centimeters. Now, I think all of the measuring devices you have go out to millimeters. So there are 10 marks between centimeter markings, which means you can go here's your centimeters place, here's your millimeters place. You can go one more. You can have an uncertainty digit. So all of those should actually have 2 decimal places behind the decimal. Does that make sense? Making sure that you keep track of that, you're going to see how you can lose a lot of precision with the Sig Figs, and so you want to make sure that when you make measurements, you make them to the precision of the instrument. Okay, so I should have given you a Sig Figs. Well, I asked you, how do you feel, what are significant figures? That was on the FIP, I think, right? Did I forget to put that on the FIP? Dagnabbit. Okay, so all of you claim you know nothing about significant figures. Not a thing. Last year was wiped clean from your brains. Okay, so you just hit reset. There's a button in the back. Okay. Every July 1st. I wish I could do that sometimes. Sig Figs are just a system for keeping track of the precision with which measurements were made. They are a huge deal in chemistry. They are a big deal in physics. And from what I hear from former students, engineers go, "Pah!" So I'm training you from the physics. I had a former student. I make a really big deal about Sig Figs. Yeah, I do. He said, I haven't had a big deal about Sig Figs in any of my engineering classes. They kind of go, yeah, that's good enough. Okay. Well, So on page 17, but if you're going to be a physics major, if you're going to be a chem major, it's a big deal. We have the rules for Sig Figs here. Okay, I know you claim to remember nothing about Sig Figs. If I show you this number, 15.23, how many of those figures, how many of those digits are significant? Just rate fingers only. Vote with fingers. Okay. All 4. You people remember something. You've never had this before. I'm going to work with you. Okay, so you all obviously remember that if it's not a 0, it's significant. When I hand you a set of measurements like this, I say it's 15.23 meters. That means whatever I measured with, was precise enough to go out to tenths of a meter. Okay. What's that, decimeters? Yeah. If I hand you that, that means that whatever I measured with was precise enough to go out to, oh wait, no, centimeters. That's what you were saying, huh? Yeah. I screw up all the time. Awesome. Yeah, so this set of measurements would be telling you that whatever instrument was used was precise out to decimeters, centimeters, millimeters. You could measure 15.23 meters with the little tiny, what is that, 30 centimeter ruler you've got in front of you. Would be a pain in the part that's challenging about Sig Figs always is the zeros, the rules for zeros. They are in your book. If it's between two non-zeros, it's significant. If it is in front of non-zeros, it's not significant. If it's at the end of a number after the decimal place, it is. If it's at the end of a number before the decimal place, with no decimal after it, it isn't. Check those. I posted the videos on Classroom. Did you all see those? The section review, numbers 1 through 4, page 19, are going to be assigned. Again, not due tomorrow. Not due tomorrow. But add that to the ongoing assignment. Let's practice a few quick Sig Fig things. So just do this on your own, scrap piece of paper, iPad, whatever you want to do. How many Sig Figs does each of these have? These are all decimals. None of them are commas. We don't use commas in scientific notation because the Germans and the French use commas like we use decimals, so we don't use them because they get confusing with international work. Which one? 4. What are other answers we have? 3.
No, I was.
No? Okay. Does everybody have 4 for this? Okay. And it's 4. That 0 is between two non-zeros. We know it's significant. Awesome. On the next one, do you agree with your neighbor? Okay. What are the answers that we have? 3, 5. What else do we have? Anybody shooting the middle ground on this and taking 4? Shoot the middle. No? Okay. So which is it?
3. I read I've never done these without pauses.
Okay, I have no legal leg to stand on, but I am going to assert my position. Okay, you can do that. I like your style, David. Okay, so explain to me why it is your answer, why you are right. Okay. Okay, explain it in more words. Explain it to them. Convince somebody who's got 5 why you're right.
They're at the end of the number on the right side of the decimal. They're not in between any other digits.
If you were to drop that, would it change your measurement?
Okay. Somebody who's got 5, convince somebody who's got 3 that they're wrong.
Zeros to the right of the decimal numbers. Only if it's
Why?
directly to the right.
That's not an argument. That's just repetition. It just is. It is. The grass is green. The sky is blue. Things fall down when you drop them. It is. Why? Look at your little ruler that you have sitting somewhere on your desk. Okay. Make an argument looking at that ruler. Silence. Crickets.
What page was the rules on?
17? Or you can make an argument looking at the rules.
Yeah.
Now we're all eagerly waiting for Katie's reaction. Either she goes, yes, or she goes, or she gives me a nonverbal. Okay, Emily?
I'm going to take kind of a guess.
Okay.
Zeros at the
I'm
end.
going to say 5 because if you got the 2 zeros, that means your instrument was so exact you can figure out it was exactly that.
Bingo.
Both zeros at the end of the number and also to the right of decimal are significant.
Yeah. So those zeros are telling you that the instrument that you measured with went out to that many places. Now, is there a difference? You're absolutely right. Is there a difference between 72.1 when you're cutting a board on the table saw and 72.100? No. You're marking it at 72.1. But if you're handing that set of measurements to somebody else, you're telling them, no, there's no fudginess in that one. That one is dead on. As a matter of fact, we could have gone 2 more digits beyond that with the instrument that we had. So that's your measurements are, I mean, they're for you, but they're also for somebody else. Remember, in science, we're sharing data, we're sharing information, so you want to make sure that everybody else who handles your data understands exactly what a rock star you are, understands exactly how well that data was obtained, understands how precise your instrumentation was, understands the limits of your instrument. If you're using, crappy, sloppy, schlocky instruments, everybody should know that. Okay, next one. Do you agree with your neighbors? Let's see. 2? Okay. Yeah, 2. At the end, no decimal after it. That's our uncertainty digit. It is not significant. So that is a pretty sloppy measurement. The last one, this is pretty much the same as the second example. How many? 5. Yeah. Okay, now let's do the more challenging thing, which is the rounding. Do you remember this? How many of you have done rounding with Sig Figs? Okay, let's take, well, I'll just give you a new couple numbers. Okay, so you're saying 10. I'm going to trust you because I can't count right now. Digits in that, and if this was a measurement that you had taken or you were given, we would say that they were all significant. Easy peasy. We've only got 1 0 in there. There's only one that's even debatable. But if this is the answer to a calculation that you've done, you have to look at the numbers that went into it and look at how many sig figs you're allowed to keep, because your answer can't have more significant figures than the measurements that went into it do. So in this case, what if we had to round this down to 5 significant figures? Well, actually, hold on. First of all, let's do the easy case. Let me add something here. Let me do the easy case. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we now have 12 places, 12 digits. And let me make sure that that decimal point is clear. What if we had to round this to 11? So at that point, we're keeping, this will be our last number. And just as a refresher, we're rounding this based on that. Your book has more complicated rules for rounding than I was taught or used. In here, we typically go with the simpler rules for rounding, which are 5 and up rounds up, 4 and down rounds down. Your book does this thing with 5s where if the next number is odd, you round up. If the next number is even, you round down, which means that over all of your calculations, you should balance the rounding up and rounding downs of 5s. We tend to err a little bit up. If any of you are going on to physics or engineering at the college level, you may use that more complicated rule. I want you to know it exists, so don't be shocked. But we typically just use 5 goes up and everything below it goes down. So how would we round this then? 7, 3, 0, 8, 2, 6, 9, 4, 3, what? 0.53. Yeah. Okay, well that's easy. Okay. A word of caution: if you're rounding, if you're working, you can't round from rounded numbers. There are situations where that will get you in trouble. We can address those as they come up. What if we had to take this number? Now let's go to the harder cases, down to 7 digits. So this was to 12. What if we had to take this down to 7 sig figs? So 1, 2, 3, 4, 5, 6, 7. This, I always underline the last digit I'm going to keep. 1, 2, 3, 4, 5, 6. Whoops. Oh, I screwed that up, didn't I? Yep. Okay. There. better. Let me get rid of this. So we are either keeping that number, we're either holding or rounding based on what comes after it, which is a 4. And what's that going to look like? So write down your answer, compare notes with your neighbor. While I find my coffee. 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 Jada jada jing jing jing. Okay, do you agree? No? Yes, no? Yes, no, yes, no, yes, no. My daughter has started doing this when she asks a question suddenly, then she goes, yes, no, yes, no, yes, no. Give me space. Okay. Who's got something? Who's got Katie? Go for it. Oh, Annie, you want to try it? You haven't tried one yet.
Sure.
Okay.
7.308269 times 10 to the 8.
Ooh, whipping out the scientific notation. Okay, I'm slow. Give it to me again. 7.308 269 times 10 to the 8. Okay. All right. 10 to the 8. Okay. Agree? Beautiful. Nicely done. We don't do that a whole lot in chemistry. We don't use scientific notation as much in chemistry. Well, yeah, we do. That's actually the easiest way to quit, to not make the most common mistake with this kind of rounding. So here's the most common mistake that people make in chemistry, and some of you have probably made this, 7308269. There's my rounded number. What's wrong with that?
43 levels.
Well, yeah. It's lacking these two placeholder. It's not 43 lower than the number. I've shifted my places. It's whatever that is, a billion lower. You know, that's like the difference between 7,276 and 72. Okay. Work on the practice. I'll post the refreshers. Oh, you've got study hall in here. You got your 4 minutes, and then you come back here. And I don't know what the deal is with cafeterias and breakfast. You want to stay in this seat? Okay, that's fine. David's got his name on his seat. Will you entertain offers of baked goods or anything? No? Lauren's like, no, I don't want baked goods. I want my seat. And yeah, you've got study hall time. You can work. We're trying to have better, more studious study halls this year, but you guys are obviously certainly welcome to be working on your physics stuff.
Should be priority number 1
In
homework. Lab.
labs due first. Labs due Wednesday. Oh shoot! I was gonna go.
Keep the grasshopper.
Oh, there it is. Hi, sweetie.
He's on the capital.
Oh, hi. We've been looking for you. Well, you know what? I suppose you could just live here. We got plants. Well, now you are really not cooperative, are you? I'm rather ashamed of my students. I'm usually better at this.
We got it.
Well, I've got my little container that was in. Here it is. And I'll just have to.
You're my hero.
Go.
There you are.
Why, was it freaking you out?
No.
Oh, okay. I didn't think so. There we go.
Pretty cool. How you gonna help?
I'm going to. I just haven't yet. Hi, Mike. You're in here for study hall today. You're in here. Yep. That was the rule that came down. You guys, I get to keep you all. Come on in. We'll figure out
It's gonna be
seating
like
stuff.
every day?
Huh?
It's gonna be like every day.
Every Friday.
Just
The Fridays. Oh, yeah.
Why Friday?
I don't know. I'm going to ask about that.
Makes me sad. I lived off the coffee shop last year. Like, lived off of it.
What is the relationship between
We do our food together. You get food the rest of it? Oh. Alright, let me know when you get through that. And I'm going to work on my chapter.
Wyatt got to be at a desk. Okay, let me help you with that. Let me get this. Okay, so we are all in here together. Right now, what I need is one person, one desk. I don't know if we have enough seats, so I want to see what it looks like. So one person, one desk, and if you do not have a desk, then I need to know that. Okay, Jillian, you have a desk and no chair? Here's a chair. So we have 1, 2 desks there. Mike, do you have a desk? Well, no. You weren't listening. I need to know if it's okay. I just need to know if we have enough desks for butts. Okay. Okay, you're going to sit there. Great. So I've got 1, 2 here. Sydney. Hi. I knew there were more of you. Come on in. I'm just trying to figure this all out. That green one is not, or that purple one is not taken. That biology book is left here. I will handle that. So I've got one there in the middle.
They have to cut it down.
Say, do you hold?
Yeah, already.
You're allowed to leave. If you want to leave, you can, and then if you need help, how about if you just stay for help? Okay, then your desk is vacated. Okay. So that's one more. Well, I'm going to try to get this there. I'm trying to keep everybody in there in study halls productive this year, so I'm just trying to play along with the game plan. There are two. Does that work? Hi, Lucas. How are you? This is like one of those logic puzzles, and I thought I had it. And then when you think you have it, then they go, oh, yeah, but the house that the person who eats lettuce in is purple. Okay. Mike, you're there. You know what logic puzzles I'm talking about? You never had to play these? Oh, my goodness. We're like, there are 5 people who live on a street. The person who likes eggplant lives next to the person who likes lettuce. The person who likes lettuce lives in the purple house. The person with curly hair lives next to the person who likes carrots. And you have to figure out all the pieces. That's what it feels like to me, except the minute that I thought I had it, then they introduced some other vegetable. Okay. Okay, Lucas? Well, okay, I'm going to have you hang there for a second. Here's what I'm going to do, folks. So I'm going to let you move. So right now, everybody except Lucas has a seat. Sorry, Lucas. This will be your Friday study hall. I am investigating whether or not we're allowed to go down to the cafeteria and do grab and go breakfast or not. I don't have an answer, and I'm not gonna do it until I get an answer. Sorry. Looking around, if you would like to move seats, you are welcome at this time to. You have to trade and negotiate. If your butt's in the seat, you own it unless you want to give it up. Same rules as when I do seat charts changes. So, you know, some of my physics folks want to stay in the desks that they were in. They own the desk. They love it. Nobody else can ever sit there. If you want to negotiate now, you can. Study hall ground rules. I'll kind of cover this. Lucas, we'll get you something. I'll steal you something. Study hall ground rules. Again, they are trying to make these more productive study halls this year. They don't want the kind of like. I know, lovely, happy, delightful chaos that was the cafeteria study hall last year, where it was all social media all the time. You guys are in chemistry and physics. You got more work to do than that. So the goal is that you're working. My typical study hall rules are no talking, no sleeping, no games. Now, with this group, a lot of you have work that you're working on in groups. You have lab packets that you're working on in chemistry. You have labs that you're working on in physics. So I'm fine with you guys working in groups on things that are group work. To that end, that was kind of why I was encouraging you, if you want to switch around and be near your lab partners, you can.
one more desk.
Connor, do you leave after this? Or do you come in late? Okay, all right. Well, here's the other thing. If any of you want to find a 1 period a week student aid posting in kindergarten or elementary or something where they just need somebody on Fridays when all the little tiny humans are all revved up and wound up and wild, if you want to go into that kind of madness. Feed them sugar, make it Friday. Okay, Lucas, let's see. For today, and you're taking off, Noelle, you're just gonna make this your, hey, I'm out of here. Okay, cool, then bye. If you wanna go, oh, you have questions, I'm sorry, okay. Hang on, Lucas, I'm gonna have to steal a chair. I'll do that in a second. Okay, let me go steal a chair.
I mean, I'm still looking to my work.
I was so scared. I want to win. I don't have
You can do that, or you can just like email me your entire thing and I'll just copy paste it together. Whatever was easiest for you to get.
We're talking about weight questions. I have no questions. I'm not just, I haven't done anything. I'm on
Hey Connor, for today, why don't you take the chair outside Mrs. Lisa's room, and Lucas, you can sit there. And then I'm gonna they took my big chair, so I'll get that back and you can be out there. All right. Yeah, and physics folks, if you've got graphs and you want me to look at them or help you with them or pick on them before you put them in, make sure. Oh, I see your job.
We didn't do it directly on the line of that.
You have to do it directly on the
Right.
That's
I know. I redid mine, so I'll have to send it to you.
So we have to switch.
It should be like, it comes out as
Yeah.
3 1/3, but you just use the points directly.
Free what? Free what?
No, I wrote.
We have the units on the wrong.
How's mine graph?
After the transaction.
Only thing I can think of is
So this is actually the. Why should I ever be out?
Is that, are we supposed to switch the?
Do I need a switch?
I'm not I mean, I just put it.
Page or-
Annie, don't forget to put your phone in.
We have to switch our independent and dependent variable one. Oh, and then, yeah.
Oh, yeah. Is that one?
I haven't seen it.
It's on that.
I should come with one.
Once you flip it.
So they all have to be.
What's you mad about? It's done.
All of,
So that's the level.
So we have to do slope again, like do the graph, and then slope
Well, if you make a different graph, we'll probably do it, but it's probably the same, you just have to switch
They're
it.
able, they all should be spun on.
Alright, who's making the graph?
Just switch the bottom number to the top. Does that work?
Measurement can be necessary.
Madison, can you go to yours and just cut it and switch?
Then your analysis, the analysis letters.
I mean, yeah, it's gonna change the graph, the slope will change.
That's the safety packet. I'll tell you what.
Yeah.
Hey Kim, because I want to make sure that you get through the lab today, why don't we punt the safety quiz back to Tuesday, and that'll be the first thing when you walk in on Tuesday will be the online safety quiz. So it should be safety packet, safety contract, and I made some paper copies of the safety packet, which I think will be really helpful to you as you're doing the lab, because it's hard to go back and forth to two documents on the iPads. You just finished something else and now you need math? Because that's their Oh my gosh.
Hey, Moser.